I should say that the title of the talk is aspirational. I'm glad I have two words in the title. Certainly the processor is open source, so we are exposing all the details for independent verification, but it's not formally verified at this point. And we think it's secure, but perhaps you guys would disagree. And I think that's part of the game here. The fact that it's open source, the fact that it's hardware implies that I think there's a level of transparency that we need in order to guarantee security, or at least give people the confidence that processors are secure. And that's a problem, I think, with most hardware that's out there. It's opaque. People don't know what the specifications are, let alone what the implementation is. And so hopefully this is not just a research project, but we hope that this embodies a research philosophy in terms of secure hardware design that will affect the community going forward. Right? So with that, let me just tell you about more specifics. I'll give you more specific details. Secure hardware can be used for lots of things. People have talked about secure network processors, which are really, in my mind, glorified encryption engines that do a lot of things in parallel. Not to say that that it's easy to build them, but the word secure hardware obviously applies to a lot of different applications. In particular, the application that we focused on with respect to Sanctum, and something that has been an application that my research group has looked at for really a decade and a half, is how can you trust remote computation? So this notion of outsourcing computation to the cloud, or some piece of hardware and software that's not in your possession, that you don't know where it is, and you do want to trust the results of that, both from a standpoint of integrity, that it does the correct thing, but also there's perhaps a privacy guarantee associated with this computation that you need. So very stylized pseudocode, really. There's some input, perhaps your genome, that's sensitive. We'll call it X. You want some function. This may be public, or it could be private, but it's an easy enough example to think of it as a public function, which is maybe genomic analysis that needs to be performed on this sensitive data X. And the result is also sensitive. It's going to tell you things about yourself or the owner of the genome. And so that X and result have to be private. It shouldn't be exposed to, or should be exposed to a minimum number of entities. There's a guarantee associated with that. And obviously, the function func has to be computed correctly. And so this is kind of, I guess at some level, the meta application. You can do what you want with respect to the specifics, but what is the trusted computing base associated with ensuring privacy and integrity here, and what are the specific guarantees in terms of the specific hardware platform that implements this, and what do you need from this hardware platform? So there's many ways you could try to solve this problem. You could try to solve this problem just using cryptography. For example, you could use fully homomorphic encryption that says that, well, you don't need to trust the hardware. That's not exactly correct. You do need, in FHE, you do need to trust the hardware to do the correct computations. And you'd have to add things on top of FHE to guarantee the integrity of computation. But certainly, there's cryptographic assumptions that say that from a privacy standpoint, you don't have to trust the hardware. And X would be sent encrypted, result would come back encrypted, and the actual hardware would never be able to decrypt, in the case of FHE, either X or the result, because it's only working on encrypted computation. The problem with FHE, I won't go into it very much, is one of overhead. So the attraction of secure hardware is we'd like to do this outsourced computation in such a way that the effort expended by the hardware is not much more than the effort expended by the client if the client were running the software or the function FUNC on his own machine or her own machine. Now, of course, I mean, it's actually a little bit better than that. The client may not have an efficient hardware platform or as efficient as Amazon Cloud or Amazon S3 or what have you could provide for you. And so you could actually get performance out of this in the sense that it's better to do this from a performance standpoint. So you have to do three things. You have to be able to authenticate this remote device. I'll talk a little bit about that. There's a secure container that you have to build. Generally, it's not just hardware. It's hardware and software that provides an environment in which you can run programs or run these functions. And together, this hardware and software has to guarantee the integrity and privacy of computation. And there's different assumptions associated with different hardware platforms. I have a little bit of a different talk that I'd be happy to give you pointers to, that talks about the spectrum of approaches from cryptography to isolated hardware and how to solve this problem. But I'm going to focus on our Sanctum project for the rest of this talk. This slide that I'm putting up is actually 15 years old. I like it. It's still relevant to some extent. And it kind of represents a research philosophy that has served as the motivation for my group for a decade and a half. And the idea is that we'd like to do this remote trusted computation by shrinking the trusted computing base, and we'd like to turn this the TCB into something that corresponds to a single chip, right? And this chip, could have software on it. I mean, you could obviously write boot ROM software and you could put it into the chip. So I don't mean to say that it's just logic gates. There's some software, and I'll say a little bit more about that as I go along here. But you'd like to say, and it's kind of nice to say this, that all we do is trust the chip, right? And that's kind of I guess it's a little bit aspirational, but that's kind of was our motivation, and starting about 2002 or so. So the reason for this is that we think that in comparison to the IBM 4758, which was a trusted computing device, that was deployed, and probably the first deployed trusted computing device 30 years ago. The 4758 protected an entire system, right? It was a disk, it was memory, it was the processor chip, obviously the software, and then it was housed in a tamper-resistant package. And it was hard, it was expensive to protect. And a single chip, it's harder to attack it physically, not that you can't do it. It's just a smaller device, and we believe that it's cheaper to protect. But you do have to store some secret keys in the chip. And Mendel is going to have a thesis defense that talks about this, and I'll say a little bit about this as well in my talk. Different from Mendel's presentation. But once you have a secret key in it, you have to protect it. And then, as I mentioned, in order to provide a software environment, you have to have some trusted software. But you don't want to trust 10 million lines of code of an operating system, Windows, Linux, what have you. You'd like to minimize that. And so you can think of this kernel as being the trusted part of the operating system. And you need to essentially be able to identify that the correct security kernel is running on this remote device to the client, which requires an attestation process, an identification and authentication process. And finally, if you're only trusting the chip and you're not trusting memory, you're not trusting the peripherals, and you can kind of see the giveaway why this is a 15-year-old slide. This is a CD-ROM, and you have a CRT up there. And as I said, I like the slide too much, so I haven't replaced it with LCD monitors and I guess USB-C connectors. There's things that you have to do with respect to this interface in order to ensure that that people, adversaries, tampering with the interface, potentially observing traffic, tampering with the traffic, taking away the memory and walking away with it, cold boot attacks and what have you, don't break the guarantees of integrity and privacy that we were trying to get in the first place. Okay. So you need to protect those interfaces. And so the three things that you have to do, roughly speaking, are authenticate the processor, essentially authenticate and identify the environment that corresponds to the hardware and software, and protect off-chip memory interfaces. We're really only talking about batch computation here. I mean, I talked about the application scenario, and it was X going over and result coming back. I really don't have the time in this talk, and to be honest, I don't really know how to solve the harder problem of interactive computation and ensuring that you have privacy and integrity guarantees when you have a user typing and there's back and forth with respect to the data going to the remote trusted device and then data coming back, etc. And so it gets very difficult because the patterns of access become a mechanism through which the adversary can attack the environment. So this is really limited to batch computation. But I'm happy to give you my thoughts on generalizing this and what the issues are, the challenges are in generalizing it after the talk. So let me talk about these three things. As I mentioned, I want to talk about work on protecting secret keys in hardware. Mendel was involved with this work, and very quickly, and I think this is arguable. What I have up here, there's people out there who think that the way to protect secret keys in hardware is to just use secure non-volatile memory, and I don't have an argument with that in the sense that there's trade-offs, pros and cons. I'll just tell you about one way of doing it, which is to use a physical unclonable function and a new kind of buff. I guess it's not new in the sense that it was published 2 years ago, but relatively speaking new. And the most interesting thing about this Sanctum processor, again, not the first time this has been done, is that the processor generates keys on its own. Essentially, you use manufacturing randomness to produce some amount of entropy, and then a public-private key pair is generated while the processor is turned on and powered up, and then the private key is unknown to everybody, I guess, save the processor itself. So essentially, it's no human knows the private key, and the public key is certified. Right? So this is nice because you don't have to have a trusted party like happens in most smart cards, where you're embedding and testing secret keys in a secure location, and there's a human in the loop, or there's other entities in the loop. So the manufacturer also does not know the private key in this case. And so here's an example of generating randomness using a ring oscillator array. And all I want to point out here is there's comparisons of ring oscillators. So the idea here simply is that when you fabricate these ring oscillators in different chips, and each of these ring oscillators oscillates at a different frequency, they're all unique. There's some granularity of the uniqueness, but you get some uniqueness, and you can compare these frequencies, and if one of them is faster than the other, let's say you get a 1. If it's slower, then you get a 0. But not only that, I do want to point out that there's some additional information that you can get out of it, which is the stability of this comparison is dependent on the environment that the ring oscillator functions in. And in particular, you have a situation where if you heat up, let's say, a chip or a device, then it's possible that because of different rates of ring oscillator frequency changes, that a 1 flips to a 0 because the faster ring oscillator became slower, or vice versa. The 0 could flip to a 1. But this subtraction, the C value, which sort of tells you the magnitude of the difference between the ring oscillator frequencies, is a good proxy for stability. Right? So if you have a ring oscillator oscillating at a gigahertz and another one oscillating at 2 gigahertz, and this is happening at, say, room temperature, and let's say you heat things up, because they're a factor of 2 apart, because there's a large difference in frequency, it's less likely that you would see a flip, that the 1 gigahertz turns into something that is in fact faster than what the 2 gigahertz ring oscillator turned into. Right? The 1 becomes, when you heat it up, let's say it becomes 0.5, and the 2 becomes 0.4, and you end up getting this flip, right? So so that's something to keep in mind, because I'm going to talk about a cryptographic construct that corresponds to a fuzzy extractor that is going to exploit this information that corresponds to the stability of a bit. So if you had 2.1 gigahertz and 2.105 gigahertz, and you compared them, and you said you get a 0 for that, then obviously it's a little bit more likely if perhaps you change the voltage or you change the temperature that you end up getting this flow. But if they're far apart, then it's less likely. Right? So that's all I'm saying here. Oh, by the way, feel free to interrupt during the talk. This is not a thesis defense, at least I hope it isn't. But so I'm happy to answer questions during. Okay, so I was told that we weren't going to be able to interrupt Mandel for the first 45 minutes by Ingrid, which is important to tell me, because in general I tend to interrupt people, but I also like being interrupted. So that's fine. So I want to tell you about fuzzy extractors, and keep this small item in mind that I just in terms of the generation of the bits. We're going to get back to it. Fuzzy extractors are a way of taking noisy sources like ring oscillators and correcting them in order to get secret keys. And this is what's called a fuzzy commitment scheme. So really quickly, you just using a true random number generator in hardware, you generate a set of secret bits S. So this is non-repeatable. I mean, every time you run this TRNG, it's going to produce different bits. But you just run it once, okay, and you get these secret bits. And you use the entropy from the biometric source, in this case a puff, which is E, and then you generate helper data, H, that corresponds to something that's going to allow you to reproduce the secret key S, which has kind of gone away. It's an ephemeral secret key corresponding to this TRNG, as I mentioned. And even though E turns into E prime, where E prime is not quite E, you can regenerate S perfectly. Right? So that's the notion of fuzzy extraction. So generate and reproduce are the two algorithms that you need. And the challenge here, and a lot of people in this room have done lots of great work in different variants of fuzzy extractors, but there's essentially a security consideration that says that you are going to have some leakage, and you have to characterize this leakage associated with exposing H. Right? So H is now, it will not be private. I mean, if you said H was private, then you may as well have stored S in that same private memory. Right? So it's kind of silly to say that H is private. So H is going to be public, and it's going to be stored on flash. It's given away. It's part of the public information. And the entropy of the secret key S, through some cryptographic assumption, information theoretic, computational, etc., you have to make an argument. You have to have a proof that says that you're not giving away all of S when you expose H. Right? So there's a lot of work on this. It's been going on for a while. And as I mentioned, there's information theoretically secure constructions. And essentially, and this is a little bit unfair, but bear with me because I have a lot to talk about, and I'm happy to answer questions about it. But I can characterize the fuzzy extractor work into information theoretic and computationally secure constructions. And the way you have it is you have to make some assumptions about the bits themselves that come from the E bits, right? And that come from the biometric source in order to prove your result that says that you didn't leak all of S, in exposing H, the helper data, right? And those assumptions you can argue with, are they really true, etc., and there's always papers. That's life, right? In research, you always criticize what comes before you in a scholarly way, but that's life. And so I'm doing that. But there's also these computationally secure constructions, which are relatively new, right? And so the original fuzzy extractor work was all information theoretic, and there were a few computationally secure constructions, but they also had issues in either only correcting a small number of bits, so you have a constant fraction of bits that could essentially flip. It's easy to see scenarios of deployed of puffs where 20% of the bits change when the environment changes dramatically, right? So it's a constant fraction, it's not a logarithmic number of bits. And a lot of the work in computational security that corrected a constant fraction of bits, they ended up making what people would say are ad hoc hardness assumptions, where you did not have a well-established problem and you didn't have crypto systems built that withstood attacks, cryptanalytic attacks for 20 years, corresponding to those assumptions. They were more, they were newer, right? It doesn't mean that they're insecure, it's just that they're newer and they're less well established, right? And so what I'm going to describe to you in a few minutes is work done, not part of Mandel's thesis, but that's Mandel out here, done by my students Charles Herder and Ling Ren and Martin Van Dyke, that essentially does a constant fraction error correction in polynomial time using well-established hardness assumptions. And again, like I said, I mean, there's going to be work that improves this. It already is, but when the work came out, I guess the fact that we managed to get it published implied that there was a delta in terms of novelty, right? But I want to tell you about it because it's actually kind of cool, and I can explain it to you in 5 minutes, right? Learning parity with errors is a sister of learning with errors, LWE. It's a simpler variant of LWE. It's a well-established problem, computational problem, and the algorithms that can solve it are sub-exponential. It's something like 2 raised to n divided by log n in terms of the best known algorithms to break this problem or to solve LPN. And I'll tell you what LPN is. It's simply a linear system of equations with a little bit of noise injected. Okay? And so that's the setup that you have here. And the way we're going to use it in fuzzy extractors is simply by saying that I'm going to set up B equals AS plus E. And the symbols that I have here are exactly what I had up until now. E is the biometric source. It's actually producing noise, okay, for the LPN problem, right? So the outputs of the puff bits are being added as noise to the LPN problem. And S is the secret key that was generated once by this true hardware number generator, right? And that's the one that you want to reproduce. And A is a public matrix that's going to be common for the entire design, all right? And so A is a matrix because S is a vector and this AM is a vector as well. So A ends up being a matrix. EM is a single bit, and BM and B1s are a single bit, right? And so that's your setup. And now, how does this work with respect to the fuzzy extractor? As I mentioned, S is secret, the A's and B's are public, and E is hidden, right? So the outputs are going to go in here. If you expose E, you're out of luck. It's as bad as exposing S. I said this already, and the main assumption that you're making is a standard assumption. It's an LPN assumption, simply says it doesn't matter how many equations I give you. So n is the number of bits in the secret, S is n bits, so that's 128, 256, or what have you. N could be 1,000, it could be 2,000, it could be 100,000, but LPN, as long as you do have some assumptions on the noise, the E bits, by the way. Obviously, they can't be constant, so they can't have very little entropy. I won't really get into that, but some fairly mild assumptions on E and many different kinds of assumptions for all of those assumptions. It's hard to discover S, even if you're given AI and given BI, for any m greater than n. Right? So you could have 1 million equations, and n could be 128, 206, or what have you, and as long as the distribution has a certain property, it's hard to invert. Right? So a little bit of noise makes this linear system hard to solve, which is actually quite surprising. So lots of crypto systems have been built using LWE, many more, but also using LPN. LWE is taking the B's are not zeros and ones anymore. They're essentially integers. Right? So that's the difference between learning with errors, which is being used to construct lots of fully homomorphic encryption schemes, for example. And LPN is kind of the less well-known, baby sister, I guess, of LWE. So how does this work with respect to what I talked about? So the setup here is simple. S is chosen randomly and is secret. The puff is going to generate the E values. And we're going to choose A randomly. And let's say we fabricated a lot of different chips with these ring oscillators, different arrays of ring oscillators in them. You can use the same A for all of the chips. Okay. Now, obviously, because the E's are different for every chip, because of manufacturing variation, when you actually power up the chip and run this for a given S, you plug in the E's, and the A's are constant, as I said, across the design, you're going to get different B's up, right? And the B's are in fact the helper data, right? So you're going to expose that helper data, right? So, so this is cool because what it says is that even though I'm exposing B, A is exposed. If the E's are hidden, then it's hard to find S, right? Because that's the LPN assumption, right? That's what it is. So now what happens when you reproduce? Well, there's a little bit of a problem here because we know that puffs have noise, right? We know that there's a constant fraction of errors that are going to change. So if you got the exact E's back, then you can just simply plug it in, and then you could get a linear system of equations, and we all know how to solve linear systems of equations in polynomial time, right? But you don't get exactly the same E's back. You get E's that are a little bit different. And of course, S is unknown. You know, the puff is going to regenerate these values on power up. All of these are known. But you know, the problem is LPN is hard even for a small amount of noise, right? So, so we haven't quite solved the problem yet. And what you need is something that is similar to a trapdoor. Okay. So what's a trapdoor here? Well, the observation that Charles and Ling had a couple years ago was simply that you have this redundancy. So I stressed the fact that n could be large. I stressed the fact that n could be 1,000,000, could be 1,000, right? But how many equations do you need, linear equations do you need in order to discover a 128-bit value? I mean, you need 128 equations as long as it's not a singular matrix. As long as the determinant is non-zero, you need 128 equations, right? So you can have redundancy in terms of the equations, and you can use the stability information that I told you about, which I also stressed, to end up picking the right equations in order to solve this 128-bit system, right? And the basic idea, it really comes down to just, you know, have 500 ring oscillators, and that's kind of the number that we use. You know, have 500 if you want a 128-bit key, you need more if you wanted larger keys. And you never expose these CIs. The C1s and the C2s are never exposed. They're not even used in the generate step, right? In the generate step, you just use the E's and go off and blast off and get the B's, right? And you put that out as public information. But in the reproduce step, what you end up doing is you have these 500 oscillators, and you get 500 values of the E primes out, right? And you don't know which of these 500 values changed or didn't change, but you do. I mean, you do, right? You have a great, at least probabilistically, you have an excellent idea as to which of these values are going to be very, 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 very likely to be the same as what were the values when S was generated way back when, okay? And so you just take 128 of the 512 values and you pick them by figuring out what the C values are, and pick the ones which have large C values, right? And the C values have changed also, right? But we're just picking the large ones. And we don't have to get this exactly right. I mean, the fact is that those 500 bits, maybe 20% of them have changed, right? Because the error rate is 20%. Maybe 30% of them have changed, right? We need to pick a quarter of them that are very likely to be the same, right? And you can do the math, and we did it to make these probabilities as low as you want. You know, for certain assumptions on the stability being a proxy, for the magnitude of the C's being a proxy for the stability, right? There's always assumptions here, right? So, anyways, that's the essence of the idea. There's a little bit of maybe a lot of detail that I'm hiding here, but obviously happy to talk about it. And there are assumptions. I don't mean to say that this is a scheme without assumptions. There are assumptions about the distribution of the puff bits that make LPN hard. There's assumptions associated with the proxy of confidence to stability, and there's assumptions associated with just the hardness of LPN and how how large n needs to be. You know, because remember, it's not 2 raised to n to solve LPN. It's a little bit worse than that, right? I should say a little bit easier than that. So all of those things have to be worked out. But you know, that's hopefully you got the idea, and there was a lot of engineering after that. Right? Good. All right, great. So essentially, I've said this, but you end up getting a situation where it's simply a choice of m in order to get this problem to the point where it's usable. So this is the puff that we are building in Sanctum. Everything that I've talked about outside of the ring oscillators is done in software. It's done in boot ROM, And so you could say, well, I need to solve a system of linear equations, etc., etc. Now, it does take time, but it's really from a standpoint of hardware complexity. We don't think of it as hardware complexity. We think of it as when the processor boots up, there's going to be obviously at some point there's going to be the generate, which is simply evaluating a system of equations, but the reproduce is obviously more complicated, and it's having the right algorithm, the correct algorithm for selection, and it's all in the trusted software of Sanctum. Okay? Yeah, go ahead.
So you choose the most stable path bits, right?
That's absolutely right.
That's the idea.
Yeah.
And I understand that that's extra information basically, and that shouldn't be cut. But did you do experiments on Hamming distances and uniqueness, choosing only the most stable bits? Because if
yes.
really stable bits, then the uniqueness
right.
might be low compared to
absolutely, yeah. No, we did that.
If the stable bit here is that the same stable bits in another.
That's absolutely correct. I mean, that's part of I think the details I'm hiding here. So originally, I mean, in terms of the analysis, there was a lot of ring oscillator data available to us, thanks to Mandel. Across many different, as it turns out, it was FPGAs and thousands of ring oscillators across, I would say, tens, if not hundreds of chips. And there was I don't know how much correlation analysis we did, but we certainly addressed this issue that you're mentioning. And I think it's fair to say that the entropy of those ring oscillators is not as high as the entropy of, let's say, the average oscillator. Absolutely correct. And what that does is it changes the values of n. You need to make it a little bit higher. And also, one other thing to keep in mind is it's a little bit interesting because in this fuzzy commitment scheme, the secret that is being generated is from a hardware random number generator. So it's all really about the computational complexity of LPN. That if the entropy was lower, as you pointed out correctly, you're in a situation where you have to analyze sort of what the 2 raised to n number is and what the computational complexity there is. So there's some amount of conservative choice that you'd have to make, and you need some margins. And it's similar to, like, if somebody came up with a better LPN algorithm, then immediately you'd have to increase these numbers as well. So it's kind of related to that. Right? So yeah, thanks for the question. So I want to switch gears. This is a computer architecture project, I guess in many senses, the Sanctum project. So I'm not going to talk about circuits anymore. I want to talk about the machine. I want to talk about how we built the processor, our philosophy in building the processor. When you have a processor, you have lots of issues associated with side channels, cache timing. I mean, you've heard of these things. In January, there were attacks done on Intel machines and AMD machines, etc. And so I really want to spend the rest of the time that I have on the architecture side of our project. But as you can see, the secure processor does need a trusted root, and I've talked to you about how we generate that trusted root. So the picture, going back to our batch computation, remote trusted computation, is a little bit more complicated than the picture I gave you before. There's actually multiple entities involved, though I have talked about them somewhat. There's a data owner that, let's say I'm the data owner, it's my genome that corresponds to this X thing that I want to have analyzed. There's a software provider, this could be 23andMe. Okay, 23andMe is going to analyze my genome. I trust them in the sense that I trust that their software is doing the right thing. It needs to be well written in the sense that it can't just take X and print it out and give it away to the infrastructure provider who I do not trust, right? And so, let's say I'm using Amazon, I do not trust Amazon, but I do have to have some trust in the manufacturer. I do not trust the manufacturer to keep the private key of the chip secret. I don't need to do that in the scheme that I've described to you. But I do trust the manufacturer to have built correct hardware. So there's no hardware trojans here. So just like this software provider could have effectively, print to scan it out of my genome, I need to trust that that doesn't happen, that won't happen. I also need to trust that there's not a hardware trojan that takes the hardware random number generator and spits out the value of S over to scan it out, right? So there's definitely trust in here as well as here. We think of it as a trust as integrity, okay? In the sense that no hardware Trojan means if I gave a manufacturer a GDS2 corresponding to a layout, they will not corrupt it, and they will do the right thing in order to build it, but there's no private information associated with the GDS2, okay? That's important to understand. So what we're building here is now a secure container, and it's got a bunch of stuff in it. You can read that. It's essentially got software and hardware. And these secure containers, you can virtualize them. There's obviously things like Docker, which are all built in software. But here we're building a secure container. It's a hardware-assisted secure enclave, right? And so there's hardware assist associated with this container. And so, again, I'm not going to go through the details here, but there is this fairly heavyweight infrastructure using public keys that is going to allow the client to attest, or you can do remote attestation. You can, the hardware, the secure container is going to attest to the client that it was built correctly. And there's a bunch of things that happen, and this is the secure container. And roughly speaking, what I want you to take away from the slide is simply that there's a protocol associated with remote attestation where you actually build the secure container. And after you've built it, you measure it using cryptographic hashing, and you say, this secure container is running on this hardware built by this manufacturer, and it was set up using this trusted piece of software corresponding to the security kernel. And by the way, I loaded all this public data corresponding to, let's say, this public data set, which is what the application required in order to run. And all of this is measured, and you end up essentially then telling the client, here's the certificate that tells you that this container was built correctly, and you can now verify on your own that these hashes match, what you expect, and then you can now send me your data, and at this point the data goes inside the secure container and can get decrypted, right? So the setup happens before the data comes from the client. If otherwise, you could have an insecure container or a fake container, and if the client just sent the data and the measurement happens afterwards, you got a problem. Right? So there have been a bunch of efforts to do this. I won't go into this, but I want to talk about Intel SGX and Sanctum. Intel SGX is deployed. You can buy SGX machines. There's good things about SGX and bad things about SGX. My student Victor Kostan, who graduated a couple of years ago, spent, I kid you not, a year and a half of his life reading the Intel programming manual and thousands of pages and about 1,000 pages of Intel patents, and wrote this document that you might have heard of called Intel SGX Explained. It came out about 2 years ago, and we put it on archive that talked a lot about how SGX was built, and I'm going to briefly give you the highlights in that document for the good parts and the bad parts. So SGX is something that says that privilege does not imply trust. Okay, so just because the operating system is privileged doesn't mean that you need to trust it. And you can get secure containers even though the operating system is malicious. Okay, so that's the philosophy to minimize the trusted computing base. And so the hypervisor is at ring 0, and so is the OS kernel, but you don't need to trust it. You're actually trusting essentially just the enclave and the application. You do trust the application to be well written, as I described to you. Right? So it's minimal in that regard, and so that's good. You can program an SGX machine more or less like you're programming a regular machine. There's a particular part of the enclave virtual address space that you're guaranteed is private, and so everything that's in that virtual address space, the operating system can't look at, but everything outside of it is public, and the operating system could look at it. Right? Public in the sense that the operating system could look at it. So you have to keep that in mind. So you copy things over. Your X, which is your sensitive data, and anything that comes from X would have to be inside of EL range. Okay, so that's nice. And then there's minimal changes in the operating system. Basically, SGX uses the page tables to isolate processes from each other, isolate the operating system from the processes. And so the page tables are going to give you this isolation. And SGX changed the hardware. This is both a good thing and a bad thing. It's difficult to take deployed hardware and modify it in the new version. The more invasive the change, and all of you who build hardware know this, there's no such thing as minor surgery, there's no such thing as minimal hardware modification, right? Or it's always painful if you want to get a new chip out of it. And so what the SGX designers were, I guess, at some level forced to do is only work on the periphery of the Intel processor and change the periphery of the Intel processor, and that's partly why SGX has so many problems. Okay, so they changed the memory controller to protect against a lot of memory attacks, and then to protect against the peripherals being attacked and the buses being tapped, etc. And they were allowed to change microcode, and they could. It is essentially SGX is implemented in microcode, and they were allowed to do that. So those are the two changes they were kind of allowed to do, and that happened in the new processors. For example, the Skylake processor in relation to the old processors. Right? So it's good in the sense that they could build the hardware by making minimal changes. Right? It's bad, as you'll see, because there's lots of attacks because they were forced to do this. Right? This was actually something that people didn't realize, that people say every time you make a memory access, you have to enforce isolation, that the operating system is not trying to make a memory access to enclave memory, or a particular enclave is making a memory access to operating system memory or a different enclave's memory. So there's this constant checking of memory accesses that needs to happen if you want security, right? So people thought that these security checks happen every memory instruction. And in fact, there were papers written that essentially said we can do better than that. But it turns out that if you actually look at SGX very carefully, that these memory checks happen only once every 1,000 memory instructions, right? And so what happens is, I don't know how much architecture you know, but TLB stands for Translation Look-Aside Buffer. It's essentially a cache, a small cache for the page table, and TLB hits are very frequent. They're a common occurrence, so you get a 99% hit rate on TLBs, and you're only accessing that once in a while, every time you move from accessing one page to another. And so when you get a TLB miss, it's a rare occurrence, and you only check these checks that I mentioned to you, which have to have some overhead associated with them, once every 1,000 memory instructions in SGX. So that's why SGX has low overhead, right? So that's important. So these are all the good things about it. And then quickly, the bad things are, I talked about open source at the beginning. I won't belabor the point. We have no idea as to what the microcode looks like. If any of you work for Intel, maybe you got to look at the microcode, but I certainly haven't, and no one I know, well, there are people I know who've seen it because they're Intel employees, but no one I know outside of Intel has seen it. So you have to take their, you have to have confidence in their ability to build all of this correctly. So SGX leaks because of sharing. I won't say much about hyperthreading, but it's a very intimate form of sharing, and so one enclave running on a hyperthreaded core can get a lot of information about another enclave running on the adjacent core. There's two cores usually in hyperthreading, and so that's a problem. People haven't attacked this because there are other attacks that are easier to carry out, and any shared resource is a potential threat. SGX leaks because of address translation. This is actually a fairly subtle point. I wouldn't call this a side channel attack. This I would call a design flaw, where the page tables in SGX are handled by the operating system. The operating system maintains all of the page tables. And on top of that, the operating system could actually write the page tables and change whether a page was cached in the TLB, whether the process knows whether the page is in memory or not. You can kind of invalidate the page. The operating system can invalidate the page. And this turned into this fairly serious design flaw in SGX, where there was a paper by Microsoft where this particular application was encrypted image search. So the idea is that your secret here is that Rubik's Cube. You have a public database and you're looking for everything that looks like that Rubik's Cube, right? And at the end of it, you want to send the encrypted Rubik's Cube over, you want to do the comparison, and you want to get encrypted image results back corresponding to the matches that you found in the public database. Right? So the secret information is the fact that this cube is this is a cube, this is a Rubik's Cube. Right? So because of this design flaw corresponding to the page tables, Very briefly, what the Microsoft researchers were able to do is essentially make the process believe that they constantly had to go to disk in order to get the pages back. So constantly create page faults. And when the process had to go to disk to get the page back, there's some leakage associated with the addresses because the operating system can see that, right? It's not just the memory, it's the page is being swapped out. And because of that, they could essentially decipher, they couldn't get the exact image out, but they could get addresses corresponding to, with enough granularity or enough resolution that they could make up this image. They say this is what the image that corresponds to the encrypted images. So in that, most people would agree that that's a break because you're getting a lot of information about the image. Right? So let me quickly go through in a minute or so other things. You've probably all heard of cache timing attacks. The fact that you're sharing the cache with another process implies that the process that is sharing the cache with you can get some information about your hits and misses in the cache based on the hits and misses that the attacking process is seeing, because you're sharing this cache, and what's happened is that the victim process is evicting data that corresponds to your data, and so you get some sense of what the data that the victim process is accessing. And this most recent attack that Ingrid and I were talking about is fairly serious. SGX, at the end of the remote outsourcing, SGX is going to use the private key to sign the results of the computation. That computation or that signing is done in software. So you're using a very sensitive information corresponding to the private key, and it's not the encrypted image or anything like that. It's actually the private key of the machine, and that private key of the machine could potentially leak through a cache timing attack. And this was conjecture, but from what I can tell, this is actually happening, right? So you can actually extract the private key of an SGX machine. I haven't seen the paper yet, based on a cache timing attack, right? So all of this is quite concerning, and so we'd like to fix these things. I wanted to mention that speculative execution is something that has attacked SGX as well, but really this EPID attack is much worse. And so I wanted, in the small amount of time I have left, I want to give you a sense of what Sanctum is, and maybe I'm going to go a little bit over, but bear with me, please. Hopefully this will be interesting to you as well. Sanctum has similar scheme. We tried to take the good parts of SGX and fix the bad parts. So similar in the sense that we trust the code and the data corresponding to the application. We trust what's inside of the enclave. And we also have some trusted software. It's not microcode. It's exposed. It's written in C++. Corresponds to the security monitor. It's a few thousand lines of code, and we trust that. And so we don't have hyperthreading. We don't have speculation. So this is a little bit of a cop-out in the sense that it's not a full-fledged processor, but it's a research project, and we do have some ideas which I'm happy to talk about offline in terms of how we could make these processors more powerful. We fixed the problem with the page tables by having two sets of page tables, and so this memory that I talked about, which is the EV range memory, the operating system can't see it, and the enclave page tables are stored inside of this protected memory that the operating system cannot see. This makes a few changes to the software, or the security monitor has to be a little bit more complex, but it fixes the problem that corresponds to the attack of the Rubik's Cube that I described to you, because the operating system cannot touch these page tables, cannot view these page tables, and can't change them. So that was an important design change. The main other thing that we do is we use cache partitioning in order to protect against cache timing attacks. And so the basic idea is as following. You can do this a couple of different ways. In a set associative cache, depending on your address, you would go here or you would go there. So given that the addresses that correspond to one enclave given that you know that the address request is coming from one enclave versus another, you can set things up in such a way that through the cache hierarchy, you have the same isolation that you have in the memory, right? So the basic idea is actually straightforward. It's not our idea. Cache partitioning simply says the top part of the cache, the first set, the first row belongs to the enclave, and perhaps the middle one belongs to the OS, and perhaps this bottom one belongs to a different enclave. And so you never have hits and misses conflicting with each other, because enclaves are only going to access the top part of the cache. There's a performance impact for this, certainly. But the operating system is not going to be touching the top set when it's running, potentially concomitantly with the enclave on a multi-core processor. Now this implies that you have to change the hardware a little bit, and these are the invasive changes that we can make to Sanctum that SGX people weren't allowed to make, in some sense. Yeah, back there.
Does that mean the first line, top line of the cache is always dedicated to enclave 0? Or what happens if there's no enclaves running?
So if you have let's say you have a multi-core processor and you have an active enclave, then the active enclave is the only one who can access the top set. But when you can certainly take the enclave and page it out. And when you page it out, you go through this process of cleaning out the cache. And at that point, a different enclave could potentially use the top set, or even the operating system could use the top set, right? But there is an overhead associated with with cleaning things out. I mean, the bottom line is, I can summarize this in really 2 sentences. There's only 2 ways you can ensure protection against cache timing attacks. Either clean up after yourself. You have exclusive access to a resource, and you clean up after yourself. You flush things after you're done. Or you do the space sharing. You have exclusive time sharing, or you have exclusive space sharing, the way I've described to you. This picture shows you the space sharing, but I talked to you a little bit about the time sharing, right? Yeah. Thanks for the question. And so the details aren't particularly important, but there's a little bit of a trick here where, because remember we're dealing with virtual addresses, you end up having to play some games associated with how you assign these cache sets to different enclave memories. So you have enclave memory corresponding to DRAM, the physical memory, and then there's other DRAM physical memory which belongs to a different enclave, and you want to make sure that these 2 pieces of physical memory map to different cache sets, right? So you have to add some hardware to it, and in particular there's a DRAM region index that is common between the cache set index and the physical page number. That's this item here. So that tells you what the region is across the memory hierarchy corresponding to an enclave. And so you could get a single region for an enclave, you could get a few regions, but they all have to be disjoint from each other. And so you can think of this as, in DRAM, you use this notion of page coloring, and you end up coloring the different DRAMs with different colors corresponding to the enclave. So the green one is here, and here, and here, and it's different from the yellow one, which is here, and here, and here. And those colors are mapped to what LLC stands for last level cache, which is the cache. And so the sets that I showed you are mapped to the colors. And you look at this, and an OS person will say, I don't like that very much, because I need to jump across these different green regions if I want to have a large frame buffer, or what have you, or maybe not even an OS person. And so it turns out we do a little bit more in terms of the hardware, where if you do a little bit of bit shifting on the DRAM index that I showed you before, you can, and this would require some barrel shifting, a little bit of shifting in the logic of the hardware. You can get contiguous regions in the DRAM as well as contiguous, obviously, cache sets. Okay? So all of these things are things that we built in hardware. Yeah, go ahead.
So what happens if you have a hypervisor actually wants to virtualize this thing?
Yeah, so if you have a hypervisor that wants to virtualize it, no, I mean, this is assuming that you have an untrusted hypervisor that wants to virtualize it. I mean, it goes back to what I said, where the process of virtualization would require essentially the enclave memory to be completely cleaned out before it was reusable by a different enclave, right? So the context switching cost when you do this the virtualization cost is the big overhead here. Yeah.
So, in line with this question, what about extended page tables? Does this 5 have extended page tables? And if so, how do you protect them?
So when you say extended page tables, do you mean multi-level page tables, or things where you have more memory than what the DRAM provides?
The mapping from host physical to guest physical memory, which in Intel processors is another 4-level page table in hypervisor mode.
Yeah, Sanctum doesn't do that. Yeah, so there's some simplifications that we've made, like no hyperthreading, no speculation. That I mean, it's possible, maybe possible to fix it, but we don't do that, right? Yeah, we don't allow that, rather. So I'm not telling you how to build an x86 system with all the functionality of SGX. I mean, I should have said that up front. Thanks for pointing it out. We're essentially doing something that we know how to do, right? Good. Thanks for the question. Right. So let me just finish up. I promised to talk about formal verification, but I'll leave that for questions. I want to just end with talking about peripherals, which is the third thing I mentioned. So there's a lot of attacks that correspond to side channel attacks. I briefly mentioned how you handle cache side channels, but there's obviously memory addresses and tampering with memory buses and so on and so forth. If in fact you wanted to protect against, for example, people walking away with memory, or being able to tap the memory bus and look at data coming over, you would have to encrypt memory. Okay, so the physical attack like that, you'd have to encrypt memory, which is easy enough to do. You'd add that to the processor. If you're worried about active adversaries that are changing the zeros and ones on that bus, and you would end up having to provide freshness, and you'd have to essentially integrity verify memory. SGX does both of these things, and a version of Sanctum does as well. And then finally, there's also observing memory access patterns. And if you want to protect against attacks that leak because of memory access patterns, you have to have a much higher cryptographic primitive, a much more complex cryptographic primitive called oblivious RAM, which we also built in a different processor. But this ends up having much more overhead. Encryption is maybe 10% overhead. This is maybe 30%. These are just rough numbers. And this ends up being factor of 3, factor of 5. And so as you want more protection, you end up having to pay more, right? We are not concerned very much in the Sanctum application of outsourced computation with physical access to memory, in the sense that we could imagine that you would have a situation where you could have other ways of doing that. People can't access the remote adversary, I should say, can't simply go to an Amazon service or go to that hardware and go tap that bus. Usually it requires physical access, obviously. So I'm not going to talk about formally verifying enclaves because I kind of ran out of time here. Sorry about that. But let me sort of summarize and give you my take on, tell you a little bit about that, and tell you about where we're at and all the limitations of our current processor. So as I mentioned, everything is open source. It's on GitHub. We plan to be able to provide an Amazon F1 instance of the Sanctum processor to anybody and everybody by the fall. You wouldn't have to build hardware. You would simply ask for, Amazon has FPGAs attached to some of their cloud services, and our project uses local hardware as well, but we're building Sanctum on the Amazon cloud, and so it's easy enough for us to provide essentially, you can think of it as an image of Sanctum, and for other people to use it. I promised formal verification. Let me say a little bit about it. So there's invariance corresponding to isolation that you can verify if you have the specification of the hardware. Everything that I talked about, at least for the second part of the talk, corresponded to isolating enclave memory through the memory hierarchy from the operating system memory and vice versa. So there's non-interference properties that are associated with this, and we have formally specified them. And on a model of the Sanctum processor, which is not the implementation, I should be clear on that, we've used temporal logic model checking to verify that these properties hold on the model of the processor, right? It's a separate problem to run the model checking or what have you on the implementation itself, but the correlation between the model, it's quite detailed. It's few thousand lines of code. The security monitor is maybe twice as big, but they're not exactly the same, right? The other thing we have to do is make sure that the measurement is done correctly, because you're doing this cryptographic attestation, and there's properties associated with that as well, right? So we have a paper on it that I'm happy to point you to, and that was work done with some collaborators at Berkeley. So take this with a grain of salt. At this point, we'd like to claim that, and the word practical is in there, that the design, either because of limited functionality, because we don't allow hyperthreading, for example, or we don't allow speculation, or because of the hardware constructs that we put in it, is secure against what we think are practical software attacks. Now tomorrow there could be another attack that corresponds to, let's say, timing memory controllers or something like that, that would cause Sanctum to fail. But that's, I think, part of the game here in putting things out in open source. I don't think that this processor that we're going to release is going to stay secure, right? But that's part of the research philosophy that we have, which is, I think, we'd like to stress to the hardware community that this is really the way to do it, and the open source software community has embraced this philosophy, as of 10 years ago, and certainly that's a thriving environment, and we'd like to see that in the hardware realm as well. And there's many things that you have to do if you want to add extra protection if you end up having new attacks that you need to modify the hardware for. Perhaps you can get away with it and it's a software modification, and that'd be nice, but obviously that's not necessarily the case, and isn't going to be the case. And I didn't talk a lot at all about performance overhead, other than touch upon it. These schemes are not, other than oblivious RAM, which is not necessary in the common case, in my view, they don't have a lot of performance overhead. They're associated with the virtualization questions that I got, associated with increasing the overhead of context switching, but encryption of the memory bus is not that hard. You can do this pretty quickly, so on and so forth. But it's not a factor of 10. It's not. It's certainly not 10%. It's maybe within a factor of 2. And so, depending on which way I tilt my head, either this is closer to reality, right? Which is kind of I'm hedging my bets here, or single chip secure processors are close to reality, right? So thank you for your attention. Thanks for the questions. Sorry to go a little bit over, but I guess professors do this all the time, right? So.
Questions?
So I heard about another project that I believe you're also involved with, Keystone, that seems very related to Sanctum. Can you say something about the relationship between them?
Yeah, absolutely. I'm part of that. Downsong is interested in developing secure enclaves. I mean, that project is 2 months old, and Sanctum is being in our heads for well, depending on how you think, 15 years or 3 years, right? So I would say that Keystone is perhaps the next generation of secure enclaves that would solve, I think, a lot of the questions that came up, and perhaps others. So it's really related to this slide here a lot. But I think I would probably focus on Keystone after we're done with this fall release of Sanctum. So I would see it as a successor. It's certainly not a competitor at this point. So. The other thing that we'd like to do, which I did mention, is threat models and use cases are intertwined. I mean, it's distributed systems, enclaves across different sockets. Certainly enclaves that are multi-threaded, multi-core enclaves. But again, what happens when you have different nodes that have enclaves in them, and you want to run a distributed application? The reason you want to use the cloud, the reason people want to use SGX is because they don't want to run that computation locally. They want performance from the cloud, right? What we've done here is, that part is actually far from reality, to be honest with you. We have a stake in the ground associated with a RISC processor that is a 4-core processor, so it's not a single core processor. but it's not a high-end server. It's not a SGX. It doesn't provide the software infrastructure that people are used to when they use Skylake, for example. And so there's a lot of issues associated with distributed security or security when enclaves distributed across processors that I think need to be addressed. And I think part of putting our processor on Amazon is we can have many instances of these processors, and now you could play a game of what would happen if you had an adversary who was snooping on the communications across these secure enclaves that are interacting with each other. And I mentioned that if we talk about batch computation, there was yet another caveat in this talk associated with the limitations of the project, the current limitations of the project, and I think we'd like to address that. And the software people don't done a lot of work on distributed system security, and so I think the Sanctum doesn't make a statement on that, but Keystone would. Mention it.
Okay.
Yeah.
When you're talking about extra charges that come with distributed systems, if you're deploying enclaves on different nodes, are you already mentioned the communication patterns, but are you thinking about other challenges?
So I think the use case is important. Absolutely, there's issues with communication patterns associated with the distributed system. But I think there's a need for defining problem definition there, right? In the following sense. So let's just say that the part that I can get a handle on is you took an application and you broke it up, and you took threads that were heavyweight threads, and you put them across different machines, different sockets, and one of them was running on this enclave, the other one was running on this other enclave, and you have this giant infrastructure, call it this distributed container, and this system software associated with the distributed container that can snoop on the communication patterns, right? So there's papers written and papers being written that correspond to making sure that the communication patterns don't leak information, right? By padding, by doing periodic communication and doing all of those things. And then they talk about the overheads associated with that. So that part I think I have some handle on. What I don't have a handle on, which I think would be very interesting, is what happens when there's a user involved, right? What happens if there's web clicks involved, right? What happens if there's a back and forth? Then you talk about completion time, potentially of enclaves or potentially of the entire application. You have to talk about the pattern of clicks and data coming back, whether you're going to force that to be periodic, what is involved with that. And so these are things that I think if you build a lightweight hardware-assisted secure enclave that has some nice properties, I feel like that's the foundation on top of which you can ask these questions and answer these questions properly. I'm not saying these questions haven't been asked and haven't been answered in some way, but I look at those answers and I'm personally not satisfied with those answers, right? So it'd be nice to get this underneath and then say, okay, in the context of this, how would you answer these questions? Right, yeah.
Would it be the same for just when you have an application running on a single system but multiple enclaves? Do you see any difference between if they are distributing different machines or running on the same system?
So it's completely a function of your trust, your TCB, right? So I feel that it's certainly believable to me that so we have a multi-core system. You can have multi-threaded enclaves even in Sanctum. Now, when you talk about sockets, you have to look at what system software. What is system software doing across sockets, right? I mean, cache coherence is an example, right? There's software, there's hardware cache coherence, which we assume is implemented correctly, and there's assumptions in our threat model associated with saying that cache coherence bandwidth isn't a side channel, right? But now, if you say that the hypervisor can look at cache coherence messages that are going across sockets, and so the same design would not scale to what you just described to me, simply because we would not be able to say that we allow that software to be untrusted, right? Because it's a little bit like the page fault thing, right? You know, like this SGX flaw. The SGX flaw was related to, as I said, you know, this design issue where the operating system could poke and prod and essentially change the application to cause all of these page faults to happen and then leak information from it. So a very similar thing could certainly occur if you had software that was controlled by an untrusted entity that was poking and prodding these cache coherence messages that are going across these sockets, and then you end up getting this leak. And to me, that's a design flaw, right? You know, I mean, you could say that's a side channel, but and maybe it is, but the point is that we can't claim that, you know, in that context. So that's kind of, you know, I think the best answer I have for that question.
Thank you for all the questions.
Yeah, thank you very much.
Let's thank the speaker again.